Hello. Happy long weekend. So I'm going to go over this picture one more time, just to sort of summarize what happened in class today. I suggest you either print out, I'm going to send this slide in an email. If you can print it out, and draw on it, that would be great. Otherwise, I would actually just draw it on your slide. So I think this slide is you really need it, and I should have printed it out. And I messed up. Alright, so again, our goal in this reaction that we're doing is to separate sodium chloride into sodium solid and chlorine gas. Okay. Now, to do that, to turn sodium, okay, into sodium solid, okay, it needs to be reduced. That sodium ion needs to gain an electron. Okay? And to do that, this reaction normally wouldn't occur without energy. So what happens is the battery generates electrons from the negative end. Okay? And these electrons travel down this usually platinum electrode. And then in the solution, okay, they combine with sodium. Okay? And this creates solid sodium. Okay? Now, because electrons are being driven this way, they're then pulled from a chlorine atom. So the electrons then are pulled through the chlorine atom and go into the battery, which then can actually finish the cycle here. But what happens when we pull electrons from chlorine? Okay, well then here, at this end, this can then become chlorine gas, right? And we're going to generate, then that's what the green sort of dots represent here. At the anode, which is a oxidation, we're taking electrons from here. Two of them can combine, okay, and make chlorine gas. Okay. Now again, the point is that you need energy from the battery to do this, because it's forcing electrons in this direction, and then pulling electrons from chlorine to make a reaction that normally wouldn't occur happen. Okay, now, we have sorry, wrong thing, guys. Alright, here we're changing up the problem a little bit, okay, and now, in this container, here, we have both potassium bromide and sodium chloride, okay, and the question is, okay, so when we have a mixture of these, okay, which reactions are going to occur? Remember, in both cases, we're taking, so we still have the same reaction, sodium chloride, and we're breaking it up into the two components. I need to balance this, so two, and now, also in the container, we have this, and we're going to break it up into its elements, and we still need to balance, so two. So now the question is, okay, well, are both of them going to break up? Is only one going to break up? So what we're going to do, okay, is we're going to write the half reactions, okay, for both that are occurring in both of these. Okay, so for sodium, right, for this one, we already did this. We have sodium positive, right, and there's two of them, okay, and it's becoming solid sodium, and there's two of them, and I forgot two of them, and, sorry, wrong thing. And we got two electrons. Okay, so sodium here is gaining electrons. Okay, we wrote this on the previous side. And now we have Cl minus, there's two of them, okay, going to Cl to diatomic 2, and it's being oxidized, so there are two electrons. Alright? And then we're going to do the same thing, okay, but now we're going to do it, and I want to change the ink color, see if that works. We're going to do it for potassium bromide. Okay, so potassium is +1, right, and it's becoming solid potassium, okay, and we have two of them, so two electrons on this side. And then here, so on the other one we have bromine, so two bromines, right, forming diatomic bromine. And then here, two electrons, we're oxidizing it to two electrons. Because again, it's going from -1 to 0, so that's an oxidation. Okay, now the question is, okay, are both of these going to occur, or only one of them? All right, now, so to figure out which ones are going to occur, I'm going to look up on that standard reduction table. So here, you should get it out. This one, obviously. I'm going to look up on this table the potentials for these reactions as I click on the wrong thing. Okay, so for this one, right, we have the sodium ion going to sodium solid. So if I look that up on the table, this is, as it was before, negative 2.71. Okay. Now this is the one it's on the fourth one from the top. It is written as a reduction, and this is an oxidation. Okay, so I have to flip the sign, and this becomes negative 1.36. So I can't read the table. And now I find this one. This is a reduction, so I don't have to flip it. It's negative 2.92. Okay, and this one here, it's also towards the top of the table. It's the fifth one down. Again, I have to flip this one because this is an oxidation and these are reductions. So it is negative 1.07. Okay. Now, the first question is, okay, so which reactions are going to occur? Okay, and it's the ones, okay, that have Sorry, someone walked into the room and I got interrupted. So it's going to be the ones that are the least negative, or so that they're closest to zero, because those are the ones that take the least amount of energy. Okay, so if you remember, let's talk about the anode, the cathode first. So at the cathode is a reduction. So which ones are a reduction? Well, this one is a reduction, and this one is a reduction. Okay, so which one of those is easier to occur? The one that is least negative. So this one is going to occur. So at the cathode will be this reaction, not this one. This one takes more energy to occur because the sign is more negative. Okay. Now, these are both oxidations. Okay. They're going to occur at the anode. Okay, so which one is easier to occur? This one. Right, it's less negative. So this one here, this one is going to occur at the anode. So if we take a look at our picture, this is what's going to happen. If we scroll up to our picture here, if I can get there, let's move it. Here we go, move the, God, not being cooperative today. So if we look at our picture, okay, and I'm just going to give up in a second because it's pissing me off. There we go. Okay, so if we look at our picture, this is the cathode. So here the electrons are going to travel from the battery, okay, and based on the one that we circled, okay, if we look at what we circled at the top, okay, we circled the one that has the energy that's closest to zero or the least negative. So here, what's going to happen is the sodium in this melted, okay, is going to accept electrons and become sodium solid. Okay, because electrons are going this way, that draws electrons. In this case, okay, it's not going to be from the chlorine, from the bromine ions in the solution. Okay, so that's going to draw electrons, okay, into the battery. And then since this is going to take electrons, this is going to form a bromine, and bromine's actually a liquid, so we won't have a gas here. Okay? But the point is that the reactions that occur, okay, in an electrolytic cell are the ones that are the closest to zero, or the least negative, because they take less energy to occur. Now, if a question asked, okay, how much voltage would we need to do this reaction, all you would do is simply add these two together. Okay, and that would tell you how much voltage you need. So if we added those two together, it'd be like 380. That's two. I don't know. So I can add it quickly. So 1.07 plus 2.71. If we added those together, it'd be 378. So you would need at least 378 volts of energy to do this reaction. Now, if you wanted to do the other ones, you could supply more and get them to occur as well. But these are the ones that would occur if you applied that much voltage. All right, I'm going to upload this video because I don't want to be rushed for the second half. The second half is about the electrolysis of water.